Yeah, so I'm Kristine. I'm from Norway. I did my bachelor and my master's degree at the Norwegian University of Science and Technology. And then I figured out it wasn't cold enough in Norway and the rocks were too young. So today I'm going to provide you guys an update from the Craton Scale Project. And the title on the program is a bit different from what I'm going to present because I will be talking about integrating the whole rock geochemistry with some isotopic mapping, but also phase equilibria. And so we're looking at the crustal architecture of the Wawa subprovince. And so I will also like to acknowledge the project research and funding partners. And here's just a little outline. And so I'll start by introducing the Craton Scale Project. And then I will proceed with an update on the progress. And then I'll show some data where we're using these large-scale geochemical and isotopic databases to basically understand the crustal architecture of the Wawa subprovince. And so then I will be showing some whole rock geochemistry and isotopic data combined and some phase diagrams. And then I will round up the presentation with a summary and some points on upcoming work. Okay, so the overall goal for the Craton Scale Project is that we wish to refine the understanding of the crustal architecture of the superior craton. And so what we want to understand is the geodynamic processes that were active during the formation of the crust. And we're also interested to look into what role these processes may have played in the localization of the many ore deposits that we find there. And so it started out with basically, what we did with the project is that we divided the superior craton into these three quadrants. And the sample collection for them were completed in two of them. And that work was done with David Mole. And he has proceeded to publish two papers. The first one was on the formation of a Neo-Archean continental crust in the southeast superior craton by two different geodynamic processes. And this is kind of like where my project comes in, because in addition to the work that he already did in the southeast and superior, we wanted to do more detail. He also last year published a paper on crustal architecture of the southeast superior craton and the controls on the mineral systems. And the new thing with the Craton Scale Project, one of the new things is that we've got a new postdoc. His name is Jacob Strong, and he is present here today. And he will continue mapping in a North Caribou terrain. And so what he will be doing is he'll do the isotopic mapping of the terrain using the lutetium-hafnium system, also performed on zircons. And so he will try to develop an overview of the isotopic character that we can find there. And then he will integrate this isotopic data with whole rock geochemistry. And so he'll start off in the summer with a field work, of course. So over to my project. I'm working, as I said, in the intro part in the southeastern superior. And so far I've collected 202 new samples. And I've mainly collected them from Wawa and Abitibi, but there are also some samples from Parika, Pontiac, the Eastern Wabigoon, and the Quetico. And so, as you can see from the numbers that are presented in the slide, it's a large amount of new data. And the figure that you can see to the right is basically just the geological map showing the sample points. The blue ones are the ones that were existing, which means the samples that David Mould used for his study. And then the yellow stars are the samples that I have collected. And so the current work on my part of the Craton Scale project is that I'm writing up my Wawa data, and so I'm looking into the crustal architecture. Okay, so now we'll move on to show some of the data. So basically, this presentation here will be mainly on the data that I have collected in the Wawa. And the focus of the study is on the TTGs. I've also collected felsic volcanic rocks, but they are not in this presentation. And as I said, most of the samples are mainly from the Wawa subprovince. Just going to put on a pointer here. They're mainly from the Wawa, But there's also some samples from the Quetico, the Eastern Wabigoon, and in the Abitibi. And I also just want to say before I proceed that the samples that I'm using in the next couple of slides, those are my TTG samples that I've collected, but there's also some samples from David Moll's study. And this highlighted area here just shows the basis for my geostatistical analysis, so when I'm making the contour maps. And so we're just going to dive in. So what you're seeing here on this slide is inverse distance weighing contour maps. And the maps are both from TTGs that are older than 2695. And what you can see is that there are two maps. One of them is for the Hf-isotopes on the zircons. The other one is on the oxygen isotopes. And so just to explain these maps a little bit, so the inverse distance weighing contour maps, like that's the first layer that you see are laid over like this area. And so you can see there are like colors that are colder and they get increasingly warmer. And what they mean is basically that these blue areas has negative or lower epsilon Hafnium values, so they're typical older crust. And then as you move towards the warmer colors, these are younger crusts, or they have like a depleted mantle source. And so I've also put in these sample points. So these are from my whole rock. And basically what they're showing, I'm not sure, it might be that the figure is a bit small for you guys, but what it's showing is that the blue color is potassic rocks, and the red colors are sodic rocks. And so what we're seeing in the Wawa for the Hafnium isotopes is that we mainly have epsilon Hafnium values that are like in the depleted mantle source field. The exception is that you see we have some like more colder colors going through, which is indicative of an older crustal component. And so if we move over to the oxygen isotopes, they're kind of showing the same thing. Again, here is a legend, and it's for the delta 18 oxygen values. And what you see is that these like browner, like more brown colors is the lighter isotopic signatures, so typical like high temperature hydrothermal. And then you have like this midfield, which is typical mantle values. And then to the bottom here, we have these whiter or light purple colors, which is the heavier values. So they're more typical low temperature systems, so probably a sedimentary component to them. And what we're seeing on the map here is that basically most of the study area is plotting inside this mantle delta 18 oxygen field. So if we jump in time, we're now looking at the rocks that are younger than 2695. And what we can see, like on both maps here, is that they're pretty different from what we previously saw. And when I say that, I mean that, first of all, we have a higher abundance of these potassic rocks. But also another thing is that like the epsilon Hafnium values are moving towards these more negative values, or the lower values, so indicating some older crust. The only exception for these younger rocks is this area here in the southwestern part, and that could indicate that we're having some younger magmatism going on there. And if we're looking at the oxygen isotopes, they're kind of like saying the same. Again, we went from something that was very mantle-like signatures, but now we're at much heavier values, and so it seemed to be a higher degree of a crustal component for the sources here. And so just like to sum things up, what we see from the oldest rock is that they seem to mainly come from a basaltic source. The Hafnium isotopes are overall juvenile, and the oxygen isotopes are indicating mantle signatures. And the younger rocks, as I pointed out, they have a higher abundance of evolved source rocks, so they're more potassic. And the hafnium isotopes are overall less juvenile, and the oxygen isotopes are indicating heavier values, so there's probably a higher degree of a sedimentary component to these rocks. Okay, so moving on from showing some whole rock geochemistry with isotopes, if we're now focusing on like the whole rock geochemistry, a very common elemental ratio that is used for TTGs is the strontium-yttrium ratio. And this is a ratio that we use mainly to infer a source depth. And we commonly say that it is a pressure-sensitive ratio. And what I mean by that is that if we have a low strontium-yttrium ratio, it usually indicates that we have shallower melts. And the way that this can be explained is that if you're at basically depths that allows a plagioclase to be stable, then if you melt that, then like since you have the plagioclase surrounding, it will pick up the strontium. And so you're left with a lower strontium-yttrium ratio. The opposite applies if you're at deeper sources. So if you melt something that's in the garnet stability field, we know that the garnet has an affinity for heavy rare earth elements, so it will tend to pick up the yttrium. And so what you're seeing on the diagram here to the right is the strontium-yttrium value plotted on the y-axis, and then have you the sodium-potassium ratio on the x-axis. And this is a figure that I've used from David Moll's 2021 paper, and it's basically based on some geochemical principles from Nguyen and Martin and Smitty's. And so what we're doing is that we're using these two whole rock geochemistry ratios to split the TTGs into 4 groups, and then continue working on that to try to say something about the source depth for these TTGs. And so what we're interested to figure out is like, how do these different groups plot spatiotemporally in the Wawa area? So is there any differences? Because if we're looking at the crustal architecture, we want to see if it evolves through time. And so you can see here, I've used the same colors as the circles in the previous diagram. And what we're seeing here is that the red indicates sodic high strontium-yttrium TTGs. The orange color is potassic high strontium-yttrium TTGs. And then you have these blue, there are sodic low strontium-yttrium values. And again, I'm showing you some contour maps. But the different thing this time is that we've used the whole rock strontium-yttrium value both as this layer on the contour map, but I've also indicated on the map what kind of like groups these TTGs fit into. So what we see here is that for the older rocks, most of the samples are plotting in this high strontium-yttrium field. There's an exception with some samples that are plotting here that are lower strontium-yttrium values. And so, you know, like what I want to figure out from this is that, okay, well, can I relate that something to, you know, the source depth and like how the crustal architecture would have been at that time? And so I've done the same thing for the younger rocks. And we can see here that like the difference is we're still having a lot of high strontium-yttrium TTGs. An interesting thing here, though, is that we have these low strontium-yttrium TTGs plotted in this southwestern area where we previously saw had these more juvenile or younger crust hafnium values. So that's interesting and something to check out. And so, yeah, like all in all, the older rocks dominated by high strontium-yttrium TTGs. We have some exceptions, and I'm going to be careful using the word trend here after Tao's presentation. But what we do see is that we have this area here that indicates that you might have some deeper sources that are trending north-south. And as we move on to the younger rocks, we don't see that trend anymore. It looks like there's probably something more east-west. And so, yeah, I introduced to you why we're using the strontium-yttrium ratio. And one of the main points that I talked about is like how a high strontium-yttrium ratio usually relates to being having a source at a depth where garnet is stable. And so what I'm showing here is just some modeling that I've done with DOG. And what we're seeing is that I just wanted to make sure, okay, so I'm talking all the time about, okay, so I have these like high strontium-yttrium TTGs. They must be coming from, you know, like a deep source. But how deep is that source? And so we just played around a little bit, and what you're seeing on this diagram is the pressure on the y-axis, and then you have the temperature on the x-axis. And we also have the depth shown here. And this modeling was done with an average caps casing structural zone mafic rock composition. So that was our proxy when we went in to do this modeling. And what we found out is that it seems like with this composition, you can have garnet stable, indicated here with the red line, around 8 to 10 kilobars pressure. So that means that you would have a source that could be at least 30 to 35 kilometers. And so we proceeded on this, and then we were asking the question if we could constrain the depths even more. And so there was actually supposedly to be a different diagram first time, but you can see it here as well. So we have the garnet plus melt field here. And then as we're moving towards higher pressure, we also get rutile. And so when we want to constrain the depths, we want to look for, okay, like, so we know that like at some point you'll hit the garnet stability zone. But that doesn't really, I mean, yeah, it helps you think about how deep the source is. But like, it's, you know, like around like 30 to 35 kilometers is pretty vague. And so if we can figure out, you know, how to put more constraints and then like say that, okay, it seems like we're in the garnet plus rutile field, then it will give us some information about if we're at like even deeper depths. And so one of the things that we will have to keep thinking about when moving forward is like, okay, what elements can we use to trace the appearance of rutile in the source rock? And so there is a lot of like TTG studies that are trying to put like the TTGs into different pressure zones. And this diagram that you see here, where we have the log strontium yttrium on the x-axis and the niobium on the y-axis, it was constructed by David Moll from a compilation of TTG rocks from Johnson et al. 2019's paper. And so they use niobium because we know that niobium, rutile sequesters niobium. So if we can say something about like the content that we have in the rocks, can we then say what pressures we're at? And like, I'm by no means saying that, you know, like that this is a perfect diagram, but it is a start. And when we're talking about low pressure, medium pressure, and high pressure rocks, one of my supervisors hate those terms. And it's basically because, okay, you say low pressure, but what is low pressure? And so that's one of the things that we are trying to figure out to be able to figure out this puzzle of the crustal architecture in the Wawa subprovince. And so just as a summary here, we see that like the majority of the TTGs seem to have a basaltic deep source. The whole rock sodium potassium do show a correlation with the zircon hafnium oxygen isotopes. And we're also seeing that there is a transition at around 2695, which that also is something that we see in the Abitibi. But for the Wawa rocks, we see that the hafnium values, epsilon hafnium values, go from juvenile to less juvenile. And then the delta 18 oxygen is telling us that we're going from mantle to heavier signature. So basically what we're seeing is just an overall like bigger transition towards something that's more juvenile until something that's mixed in with some crustal components. And from the phase equilibrium modeling, we are indicating that the garnet stability starts at 8 to 10 kilobars. So that's about like 30 to 35 kilometers depth. And we are also showing that there is spatial and temporal variability of the crustal architecture across the Wawa subprovince. And so what we will be continuing to do is to integrate the zircon trace elements with these data. We also will include the felsic volcanic samples. And of course, it requires further phase equilibrium modeling of samples from the northern part of the Kapis-Casing structural zone, because the one that I showed is from the southern part. And so we want to see if they differ. And so to check if the garnet stability zone can be assumed to occur at the same pressure and temperature conditions throughout. And we also want to further test the variability of bulk composition and its impact on garnet, amphibole, and rutile stability. And so, yeah, we're investigating if the crustal architecture of the Wawa subprovince is similar or different from the Abitibi subprovince to see if these similarities or differences can explain the localization of the mineral systems. And so with that, I'll just like to say thank you.
Thank you, Kristine. We do have time for a question.
Yeah, Kristine, why did you choose 2695 as your limit between one group of tonalites and younger groups of intrusion? Because given that within like a big difference between, which you didn't mention, between the Wawa and the Abitibi is the presence of Isoarchaea within the Wawa. So there is a whole group, different ages of rock, of intrusion
Yeah.
within the Wawa.
Yeah, so the reason for that is, so we have tested out, like doing like this contour mapping and changing, like the time. First of all, like there is, we can see from not just like the isotopic mapping that we do, we can also see from like the trace elements in the zircon that something is happening around there. And so that's why we take that as, okay, here we do see a transition. Like we don't see that transition at like different times so clearly. So that's why it was picked.
I couldn't quite read the scales on your.
Yeah, I apologize for that.
So when you say the epsilon hafnium values were less juvenile
Mm.
in the post 2695, you just mean they were actually less juvenile in their absolute values, or just you had less samples that had juvenile signatures?
No, less like epsilon hafnium, yeah, like the trend, yeah,
Okay.
yeah.